Good morning. In the last video lecture, we saw that if the canonical generator for a cyclic code of length n has degree n minus k, then the cyclic code has dimension k. Moreover, we can write down a generator matrix for the cyclic code by taking the coefficients of the canonical generator g of x and k minus 1 of its cyclic shifts. In this lecture, we'll study the dual code of a cyclic code. We'll prove that the dual code is also cyclic, and we'll determine its canonical generator. Let C be an nk cyclic code over a field F with canonical generator g of x. This means that g of x is monic, it has degree n minus k, and it's a divisor of x to the n minus 1. I've written out g of x here as a polynomial of degree at most n minus 1. Since g has degree n minus k, these coefficients on the right are all 0. Also, since g of x is monic, the coefficient gn minus k is equal to 1. And finally, the coefficient g0 must be non-zero, because if it were 0, this would mean that x divides g of x, which is impossible since g of x divides x to the n minus 1, whereas x doesn't divide x to the n minus 1. Definition: the parity-check polynomial of C is h of x, which is defined to be x to the n minus 1 divided by g of x. H of x has degree k, it's monic, and it's a divisor of x to the n minus 1. I've written h of x here as a polynomial of degree at most n minus 1. Since h has degree k, these coefficients on the right are all 0. Since h is monic, hk is 1. And since h divides x to the n minus 1, the constant coefficient h0 is non-zero. I'll next define the polynomial a of x to be g times h modulo x to the n minus 1. And I've written out a of x here as a polynomial of degree at most n minus 1. But now g times h equals x to the n minus 1, which is 0 modulo x to the n minus 1. So in fact, a of x equals 0, which means that all these coefficients are all 0. Nonetheless, I'll equate coefficients of x to the I of both sides of this equation for all I between 0 and n minus 1. As I've noted, the coefficient of x to the I of the left-hand side is ai, which is 0. Now, when you multiply g of x and h of x together and reduce it modulo x to the n minus 1, you get several terms in x to the I. So when you multiply the constant term in g with the degree I term in h, you get an x to the I term with coefficient g0hi. Similarly, the linear term in g times the degree I minus 1 term in h gives you a coefficient g1hi minus 1 of x to the I. And when you multiply the degree I term in g with the constant term in h, you get the term x to the I with coefficient gih0. Also, when you multiply the degree I plus 1 term in g with the degree n minus 1 term in h, you get this monomial, and since x to the n is congruent to 1 modulo x to the n minus 1, I can replace x to the n by 1 since I'm working modulo x to the n minus 1. So in fact, the product of these two monomials gives you a degree I term, whose coefficient I've written down here. And similarly, you get these other coefficients of x to the I in the product of g times h modulo x to the n minus 1. Now, when you look at this expression for I equals n minus 1, you see that it's the inner product of the vector g, whose components are the coefficients of g, and the vector h bar, whose components are the coefficients of h, but written in reverse order. Looking at this expression when I equals n minus 2 tells us that the vector g is orthogonal to the left cyclic shift of h bar, and so on. Hence, the vector g is orthogonal to the vector h bar and all of its left cyclic shifts. And thus, g is orthogonal to all right cyclic shifts of h bar. Since the vector g is orthogonal to h bar and all cyclic shifts of it, it follows that all cyclic shifts of g are orthogonal to all cyclic shifts of h bar. I'll remind you that h bar is the vector you get from the coefficients of the polynomial h bar of x, which is the polynomial h of x with its coefficients written in reverse order. We had the following generator matrix for the code C. The matrix G here is a k by n matrix, whose rows are the coefficients of g of x and k minus 1 of its right cyclic shifts. Let's define this n minus k by n matrix H. The last row of H are the coefficients of h bar, and the rows above it are successive left cyclic shifts of the last row. Now, from the above observation, we know that every row of G is orthogonal to every row of H. And hence, every row of G is orthogonal to every column of H transpose. And this means that G times H transpose equals 0. It follows that every linear combination of the rows of H is orthogonal to every linear combination of the rows of G. And hence C primed, which is the code generated by the rows of H, is a subset of the dual code of C. But now the rank of H is n minus k, because recall that hk is 1, and so the matrix H has n minus k leading ones. Thus, the dimension of C primed is n minus k, which is also the dimension of the dual code of C. Finally, since C primed is contained in C perp, and they have the same dimension, it must be the case that C primed equals C perp. And this shows that H is a generator matrix for the dual code of C, and thus H is a parity-check matrix for C. I'm ready now to prove our main result, which is that the dual code of a cyclic code is also cyclic. I'll need the following definition. Let H be a polynomial of degree k. Degree k means that the leading coefficient hk is non-zero. The reciprocal polynomial of H, denoted hr, is defined to be x to the power k times h evaluated at 1 over x. You can check that this expression is this polynomial of degree at most k, whose coefficients are the coefficients of h, but written in reverse order. Note that the leading coefficient hk of h is now the constant term in the reciprocal polynomial, whereas the constant term h0 is now the coefficient of x to the k in the reciprocal. If h0 is non-zero, we define the polynomial h star of x to be h0 inverse times the reciprocal of h. When you compute this product, h0 inverse cancels with the h0 here. And so h star is a monic polynomial of degree k. Informally, h star is the polynomial you obtain by reversing the coefficients of h and then making it monic. By making it monic, I mean multiplying the polynomial by the inverse of its leading coefficient. Here's our main theorem. Let C be an nk cyclic code over the field F with canonical generator g of x. Let H be the parity-check polynomial of C. Then C perp is cyclic with canonical generator h star of x. Let's prove the theorem. we have g times h equals x to the n minus 1. Replacing x by 1 over x gives us this expression equals 1 over x to the n minus 1. I'll now multiply both sides of this equation by x to the n. On the right-hand side, we get minus xn minus 1. And on the left-hand side, I'll split up the x to the n into x to the n minus k and x to the k. Now you'll recognize this expression as a reciprocal of g, and this expression as a reciprocal of h. And so the product of these reciprocal polynomials is minus x to the n minus 1. And this shows that the reciprocal of h divides x to the n minus 1. Since h star is just a non-zero constant multiple of the reciprocal of h, it follows that h star is also a divisor of x to the n minus 1. In fact, a monic divisor of degree k. The cyclic code generated by h star has a generator matrix, which I'll call h star, whose rows are the coefficients of h star and n minus k minus 1 of its successive right cyclic shifts. Now we saw a very similar matrix on the previous slide. Recall that we had this n minus k by n matrix, whose rows are a basis for a code C primed. We'll recognize that the first row of h are the coefficients of the reciprocal polynomial of h. And the remaining n minus k minus 1 rows are right cyclic shifts of the first row. Since h0 is non-zero, its inverse exists. So I can multiply the first row of h by h0 inverse to get the coefficients of the polynomial h star. I'll do the same for the other rows of the matrix H. The new matrix has as its rows the coefficients of h star and n minus k minus 1 of its right cyclic shifts. Now, multiplying the rows of a matrix by a non-zero constant does not change the row space of the matrix. And hence, the row space of the matrix H equals the row space of the modified matrix H star. But we saw that the row space of H is a dual code of C. Hence, the row space of H star is also the dual code of C. And this proves that the dual code C perp is cyclic and has canonical generator H star of x.
In the next video lecture, we'll derive an especially nice parity-check matrix for a cyclic code, and then we'll see that computing syndromes, with respect to this parity-check matrix, has a nice algebraic interpretation. So this will be in V5e, and we'll see you then.